Good morning, how are you doing? I'm Mr. H. Thank you for joining me. In this video, we're looking here at a good, easy example, and we're demonstrating the difference simultaneously with the midpoint and the trapezoidal rule. You don't have to pick a very difficult function because for most functions out there, for the practical ones that you will deal with, there is a derivative, antiderivative, all of that in terms of a template available. You have a good integral procedure for those types. You are using these rules or these approximate integration techniques in those rare instances where you have no other means available. When you're looking over here at sine x from 0 to pi over 2, 0 to 90 degrees, the area below the curve is very easily determined. You have an antiderivative here, minus cosine x, and you go from pi over 2 to 0. You do a minus cosine of pi over 2 is a 0, but cosine of a 0 is a 1. You get an area below the curve which is a 1. And I want to save that over here, this value 1, as a reference, because now what we're going to do is look at it in terms of the midpoint rule, MR, and then we'll look at it here with regards to the trapezoidal rule, TR, and you'll see that the techniques are not hard. The trapezoidal rule is a little more tricky in terms of understanding, but it's not hard. All of this obviously can be done without having to draw the rectangles and doing a depiction of how your Riemann rectangles are, the endpoints and all of that. You can just get right into it. You know, we're looking at everything here from 0 to pi over 2. We'll start with this interval, the width determination. You'll do b minus a over n, and let our n over here be a value of 3. The larger the n value, the more accurate, but we can go with pi over 2 minus 0 divided by 3. You have a pi over 6. That tells you each interval is 30 degrees. If you want to keep everything simple, we can. Just so long as you remember to keep your calculator on the degree mode. We have our interval, we'll have our midpoint value, and then we'll have our f of xi, which you know is your sine x. Everything here on the DEG mode, degree mode. We don't have to go by radians, we can just do 0 to 30, and then we can do 30 to 60, and then we can do 60 to 90, because everything is going here by 30 degrees. Might as well keep these type of numbers versus bringing the radian format numbers, because that would be difficult. The middle of 0 and 30 is 15, because you're doing midpoints over here. Middle of 30 and 60 is a 45, middle of 60 and 90 is a 75. Here all you're doing is basically putting those values in the function to get your lengths of each of those rectangles. Sine of 15, sine of 45, and sine of 75. All you have to do is add this and multiply it by delta x, but here delta x is still pi over 6. You're not multiplying by 30. Converting that into degrees, you're multiplying by pi over 6, so don't make that mistake. Here I'm just using everything in degrees, but this right here is still in radian format, pi over 6. So let's do this. We'll do everything here in a single step on our calculator. We'll do 15 sine plus 45 sine plus 75 sine. We'll multiply by pi, and then we'll divide it by 6. We have here a 1.0115 representing the area of this specific representation. Here it'll be 1.0151. You can see it's slightly larger than the true value here of a 1. Keep in mind, sometimes the midpoint rule will be overestimated slightly, and sometimes the trapezoidal rule will be overestimated. In some instances this will be underestimated, in others this will be underestimated, but in general the midpoint rule is always slightly more accurate than the trapezoidal rule. Now we have a value over here, 1.01151, determined from the midpoint rule. If you take the true value of the area of the curve determined by integration, we know it was 1. You minus it from what you have over there, 1.01151. We're off by minus 0.01151. We can write that here, we're off by minus 0.01151. And then we can compare that. That will be our error right here, my error, my amount of error. Then we'll compare that with the trapezoidal. You find out that the error amount here is much less than that for this, because this is generally slightly more inaccurate. Trapezoidal rule, let's look at that. You still have the delta x, you'll have it over 2, and then you know you're going to have f of x0 plus 2 f of x1 plus 2 f of x2. Well, how far do we have to go to? It's not hard, I've told you that. You have an n value of 3, you always do n plus 1. So therefore you'll have 4 terms. And then finally your last term, which is f of x3. You know the terminal terms always have a coefficient of 1. The intermediate terms always have a coefficient of 2. You have a delta x over 2. We have a delta x already. Pi over 6 over 2 is a pi over 12. I have everything here in terms of these values, intervals right here. Here's my x0, here's my x1, x2, x3. Everything is seemingly coming off from right there. And even if it wasn't, you would still do the same interval determination anyways. F of x0 would be sine of 0, because our function here is sine x, plus 2 times sine of 30, plus 2 times sine of 60. Remember, here we're not doing midpoint values, we're taking the real values here. Here we're doing the midpoint values, the midpoints. Finally, we have a sine of 90. You have to do this entire computation and you'll have a value relatively close to 1, but let's see what it is. I'm going to do these intermediate values first because I know what the values here are. Let's start with 60. We'll do 60 sine, we'll multiply it by 2. Plus, I know sine 30 is a 0.5. 0.5 times 2 is a 1. I'll just add 1. I know sine 90 is a 1. Plus 1. Sine 0 is a 0. We'll multiply this now by pi and we'll divide it by 12. I have a value here, 0.977048. That represents the area of that region below the sine curve from 0 to pi over 2 using the trapezoidal rule. Now I've saved this value and let's take that 1 and we have a 0.02295. I'll put it right here, a positive 0.02295. For my error determination, I'm minusing my true value minus my approximated value. My true value here is a 1. I'm doing minus 0.977 from that 1. I'm getting this. In this instance, the midpoint rule, my true value was 1, but my approximated value was larger. Hence, I'm getting a negative here. Here, I'm getting a positive. You can convert these into percentages if you want. You don't have to, but look, the trapezoidal rule is like a 0.022 amount off. This is 0.011 amount off. This is twice as off as that. That's twice as close or twice as more accurate compared to this. You can do 0.02295, the error from the trapezoidal rule, divide that by 0.01151, the error from the midpoint rule, and you'll have a value 1.99. So this right here, even the discrepancies are very minor. This was still twice as more accurate as this in terms of the error amount. But that right there brings us to the conclusion of this video. You can see the midpoint rule and the trapezoidal rule, they have their own basic techniques. This generally tends to be more accurate than that. But in some instances, this will overestimate. In some instances, this will underestimate the actual, with regards to the actual area. These approximate areas can either flip or flop based on the type of function you have and the interval you have. But that's it for this video. If you have any questions, ask me. Thank you for watching. Have a nice day.